Hi guys, welcome to part 4 of our 4-part series on NMR spectroscopy. And today we're going to be talking about carbon NMR spectroscopy. So, as you know, any nucleus with a nuclear spin can be studied by NMR spectroscopy, and for a given magnetic field strength, different nuclei absorb different energy in different frequency ranges. And so the NMR spectroscopy of carbon is called the carbon NMR or CMR. The only isotope of carbon that has a nuclear spin is carbon 13. So as we know, the atomic number of carbon is 16, and the three isotopes that you possibly are familiar with, probably the most familiar with carbon 12, but we have carbon 13 as well as carbon 14. So we know that carbon 12 and 14 have no spin because they have even mass number, even atomic number. And carbon 13 is the nuclei or isotope of interest because it has spin I, which is equal to a half. It has an odd mass number, even atomic number. And so because of that, it will display the NMR phenomenon. And it's important to also note that carbon 13 has a natural abundance of 1.1%. All right, so as we just mentioned, the relative abundance of carbon 13 is about 1.1%. The magnetogyric ratio for the carbon 13 nucleus is about 0.25 of the proton nucleus, which means carbon 13 nucleus has 0.159 the sensitivity of the proton nucleus. In other words, the carbon 13 is less sensitive than the proton. So because of these two factors, carbon 13 spectra are about 0.0002 times as intense as as proton spectra. So for weak signals, signal to noise is increased by averaging out the signal from multiple scans, and the noise averages to 0 and the signal increases. So this might not make much sense to you right now. However, you would be able to actually pick it up, or you would be able to look at the signal. So again, when we think about NMR spectroscopy, we ought to be thinking about lines or signals on a spectrum. And sometimes you see noise that would be, in competition with your signal. So what we're saying here, for weak signals, that is for signals that are not as intense, signal to noise is increased by averaging out the signal from multiple scans. And so the noise averages to 0, and in this situation, the signal increases. All right, so as we mentioned, the spin of proton is a half, spin of carbon no spin, and carbon 13 spin is equal to a half. In terms of the natural abundance for proton, 99.9%, carbon 13 1.1%. So again, significant information here. 1.1% of all carbon nuclei are carbon 13, and so the external magnetic field strength is represented by this, the magnetogyric ratio, and we're familiar with these equations already and these terms, and it's really significant here to look at the difference in energy between the carbon-13 and the proton signal here, and we can see that is quite, the difference between proton and carbon is quite significant. And so we would expect the NMR signal for carbon-13 to be very weak. However, there are now very powerful and efficient methods of generating and collecting NMR data. That's FT, Fourier transform, NMR. The low abundance of carbon-13 is no longer a serious problem. All right, so another thing that we need to mention is coupling and splitting. And this won't be a big issue with carbon-13 spectroscopy, but we need to at least mention it and mention why it won't be a big deal for this type of spectroscopy. Well, coupling or splitting between carbons generally is not observed. So let me repeat that. Coupling or splitting between carbons generally is not observed. The reason is the low natural abundance of carbon, which we mentioned several times, making it unlikely that two carbon-13 nuclei will reside next to each other in a given molecule. So attached protons, however, with a spin of a half will couple with carbon-13 nucleus to generate spin coupling, right? So the signal from the carbon will be split into n+1 peaks, where n is the number of attached protons. So the splitting, and we're going to talk about now carbon-13 coupling and decoupling. So the splitting of carbon-13 resonances by protons is so large relative to differences in chemical shifts that it can be difficult to distinguish between different peaks and peaks that are split by coupling. And so spectra can be obtained in proton noise decoupling mode, wherein which the sample is irradiated at a second frequency, which promotes all of the protons in the molecule to high spin states, disallowing the spin coupling process. So all of the split carbon-13 signals are thereby reduced to sharp singlets. So in carbon-13 spectroscopy, the signal for deuterated chloroform, that is carbon-13 coupled to deuterium, and of course we know that that is deuterated chloroform, one of the most common solvents used for NMR, and it has an odd number, even mass, so I is equal to 1, and the coupling, which is S, is equal to 2Ni plus 1, and so coupling of a magnetic nucleus, for example, or carbon, to N equivalent nuclei with spin I will split the signal from A, which is, for example, carbon, into a multiplet consisting of 2Ni plus 1 peaks. And so to predict the multiplicity of the signal for the carbon in CDCl3, we get S is equal to 3. So that means that N would be equal to 1 and I would be equal to 1. So that would be equal to 3. So the multiplicity of the carbon signal in deuterated chloroform is a triplet. So the signal for the carbon atom in CDCl3 appears as a triplet centered at 77 ppm. Right, so anytime you see a carbon spectrum that is run, if the solvent is deuterated chloroform, you will most definitely see a peak at around 77 ppm. Continuing on the carbon-13 coupling and decoupling, so while this operating mode provides less information than the non-decoupled mode, it is commonly used because it results in a significant signal enhancement due to a phenomenon known as nuclear Overhauser effect, NOE for short. NOE enhancement is not uniform, hence the integration of a carbon-13 spectrum is typically meaningless. And so spectra in which proton coupling has been eliminated are called proton decoupled carbon NMR spectra. And those are the spectra that we will be looking at for this course. So I know we mentioned previously the splitting of carbon with proton, but the spectra that we will be looking at is proton decoupled carbon NMR spectra. So essentially they are spectra in which proton coupling has been eliminated. So they all just look like, so it just look like singlets. All right, so here we have an image of a carbon-13 proton coupled spectrum and a carbon-13 decoupled from hydrogen spectrum. So, you know, we're not even going to go into this very much, but clearly it would be very difficult to interpret this spectrum, right? So we have our quaternary carbon here, and we have, you know, our different peaks here. So we have, you know, quartet, triplets, etc. And that is the proton that is on the carbon splitting the carbon signal, as compared to a proton carbon-13 decoupled from hydrogens. We just have singlets, right? So this peak, you know, looks less complicated. You know, we just have singlets, and each line represents a carbon in a different electronic environment, right? So we're simplifying it basically. We're not doing, you know, the carbon-13 proton coupled for this course. We're looking at carbon-13 decoupled from hydrogens, which we will see just spectra that look like this, the singlets, no splitting of carbon. So again, we have some other examples. You know, this is toluene, and you know, we can see the toluene without proton decoupling looking very complicated, while carbon-13 with proton decoupling, you know, it's just looking so much easier. And of course, we have our chloroform here, deuterated chloroform at 77 that we mentioned. That's our solvent. And we have our methyl here, and we have our aromatic. So our methyl protons are in this region, and our aromatic protons are in this region here. We have our quaternary carbon here, and our C aromatic hydrogens, sorry, carbons here. This is a carbon-13 spectrum. So we only focus on the carbons in this spectrum. All right, so our carbon-13 chemical shifts, the range of chemical shifts is large compared to that of proton NMR. Trends in carbon chemical shifts parallel those for proton chemical shifts. That is, you know, if something is shielded or deshielded, you know, it's upfield or downfield, so that kind of trend. The chemical shifts in the carbon NMR are more sensitive to small changes in chemical environment. So this is an example of our proton NMR and our carbon NMR, right? So we have our splitting that we are familiar with, and at this point we should be able to look at this spectrum and figure out the structure, or look at the structure and figure out the spectrum for this very simple molecule. And this is the carbon NMR, right? So clearly the trends are similar. So I'm pretty sure that the carbon that is attached to the electronegative atom is this one, and then that would be followed by the carbon that's attached to that carbon, etc., etc., right? So the trends are pretty similar. So this carbon here would be the most de-shielded, and so that is why it's 60 something, and this methyl would be the most shielded, and I'm sure that is why it would be the most shielded. So as we did for our proton chemical shift, you need to also be familiar. You will not be getting a chart for the final exam, so you need to be very familiar with your proton chemical shift as well as your carbon-13 chemical shifts. So just to know your values. So in this case, our carbon chemical shifts, as we said, it's a longer range. So it goes from 0 to, here we have 220 ppm, right? And so, these carbons are reflective, or, of the electronic environment that they're in, or alkanes are more shielded and more, upfield. And, clearly we have some electronegativity here, and so they would be more de-shielded. All right, so can carbon NMR signals be integrated? Because we have seen integration and it has been so useful for us in proton NMR. And the short answer is no, not unless special techniques are used, and we're not going to go into those special techniques. It's noteworthy, though, that the intensity of carbon-13 signals for quaternary carbons is generally low relative to, or methane, methylene, or methylene or methyl. So just to point out here that our quaternary, what we mean by that, the intensity of our quaternary carbons being low. So in this structure that we see here, we have two quaternary carbons, right? And here they are less intense than our methylenes and or methyls, right? So that's the point here. So just to mention that our quaternary carbons are have a less intensity than our CH2 and or CH3. All right, so spin-spin coupling tells how many protons are attached to the carbon nuclei, that is primary, secondary, tertiary, or quaternary carbon. Carbon-30 spectra are usually collected with the proton or carbon-13 coupling turned off, and as we mentioned, decoupled. In this mode, all carbon-13 resonances appear as singlets, as we have seen. So as we did with our proton application, we're going to now look at some examples for our carbon NMR. All right, so example 1. How many signals are expected? And the question might sound like this. How many signals are expected in the decoupled carbon-13 NMR spectrum of butyl acetate? So if you know the compound, for example, and you know the structure of it, then essentially what you're trying to figure out here is how many electronic environment is present, right? So let's see. If we have 1 here, 2 here, 3, 4, 5, 6, let's see if the spectrum is in agreement. So we have 1, 2, 3, 4, 5, 6. So we are in agreement there. So there are a couple of signals that should jump out to us, or ester carbonyl, and pretty soon you'll be able to know the relative numbers. So our ester carbonyl here is at around 170-ish, and our carbon here that is bonded to our electronegative oxygen is in the 60 odd region. And then of course everything else is more shielded, and I'm pretty sure this methyl here would be the most shielded in the 10 to 20 range in terms of ppm. But that isn't the question. How many signals are expected? And if you counted 1, 2, 3, 4, 5, 6, you'd have answered that question. All right, so again, how many signals are expected in the decoupled carbon-13 NMR spectrum of 3-bromotoluene? All right, so go ahead and count the different electronic environments. All right, so if you counted 7, then you would have been onto something. So we have 1 here, which would have been the most shielded carbon, that would be here, 20. And we have our aromatic protons, so we have 6 of them. So all of them are in different environments because we don't have a symmetric molecule here. So we have 6 carbons plus 1, 7. So 1, 2, 3, 4, 5, 6. So here we have all 6 aromatic protons being in a different environment from our methyl. So we have 7 signals. All right, so how many signals are expected for this particular compound, 1-methyl ethyl propanoate? All right, so let's see. Well, take a second to figure it out. All right, so let's see. 1, 2, 3, 4, 5. So we expect to see 5 signals. 1, 2, 3, 4, 5. So again, our ester carbonyl would be in the 170 region, or carbon that is attached to something that is electronegative is in the 60 to 70 ppm region. And then the others clearly would be shielded in comparison to those. But clearly we have these 2 methyls carbons would be in the same environment, so that would be 1. And then we already counted that already. And then we have this one, this methylene, and we have our methyl. All right, so another type of question: which of the following is the spectrum for ethyl isopropyl ketone? So you want to take a second to just look closely at the number of signals and where the signals are. So here we have our solvent peak, so that means this compound was dissolved in deuterated chloroform and the spectrum is either A or B. All right, so what you want to look at is, look at the compound to see how many signals, firstly, would you expect. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 1 you know, that might not help us this time around because both spectra has 5 signals, right? So, but the first thing you want to think about though is how many signals would you expect? And in this case, that information will not help us. All right, so in this case, what we need to know is our table, right? So we have a carbonyl peak here, or we should be expecting. This is a ketone carbonyl, and we want to just look at our table and to see where that carbon would resonate, right? And I'm sure when you look at that table, you will see 200 and something ppm. So that is pretty much a dead giveaway in terms of, you know, once you know your numbers and have an idea of where your peaks are, then you would definitely answer this question with ease. So just by looking at the table and knowing that your carbon would be in the 200 regions and that is absent from B, then you know for sure that the spectra could not be B and it must therefore be A. All right, so another question: match each spectrum to the isomers of xylene. So we have ortho, meta, and paraxylene here, and we're told to ignore our solvent peak at 77 ppm. All right, so I think one important thing that we need to do firstly is to draw our lines of symmetry. So let's do that. So I think, and pardon me for my less than straight lines. So as we can see here, guys, for the first two, that is the ortho and meta, they have one line of symmetry, and for our para, we have 2 lines of symmetry, right? So I think that is the key in deciphering which is which, because once we draw our line of symmetry, then we know which carbons are in the same environment, right? So which one is the, all right, so let's go with the easiest one, the one that has the most lines of symmetry. All right, so clearly we would have a methyl, would expect to have that in one environment. Would expect to have this quaternary carbon in one environment, and then would expect to have our methylene or aromatic proton here in another environment. So in essence, we would expect to see 1, 2, 3 signals for our paraxylene because we have 2 lines of symmetry. All of these carbons would be the same. All of our CHs or aromatic protons would be the same. Because we have a line of symmetry here, this quaternary carbon would be equal to this quaternary carbon, and our methyl would be equal to our methyl, right? So I think the easiest one would be A for our para. And so now we need to figure out our ortho and meta. All right, so let's do our ortho first, right? So we have 1 line of symmetry. So therefore, we would expect that our methyl would be in one environment, this quaternary carbon would be in one environment, this and this. So we would expect to see 1, 2, 3, 4 carbon peaks for our ortho isomer. And then let's see if the meta one matches up to this one. So if we have this line of symmetry, that means that this carbon would be a particular number, this quaternary carbon would be a particular number, our methyls. So we've gone 1, 2, and 3, and then we have these 4 and this 5. So we have 1, 2, 3, 4, and 5 here. So clearly that would correlate to our meta isomer, right? So in this case, you know, with first thing we draw our lines of symmetry, lines of symmetry, and that will establish for us which carbons are in similar electronic environments. All right, so example 6, and the question might look like this. Suggest a structure for the compound C5H10O2 using the following data. So whenever you see a formula, I would suspect the first thing that you want to do is to calculate your DBE. So what is your DBE? Try to calculate that first. And then you're given all of this data that, you know, you have a quaternary carbon that's 180.8. So check your table to see, you know, what kind of functional groups are in the 180.8 region. And then, you know, clearly we have some methylenes and a methyl here, right? So, you know, if you proposed something like this, then, you know, and I'm sure when you checked, you calculated your DBE. Well, the DBE for this clearly would be 1, right? But you should still calculate it since you're dealing with an unknown, or you should have been dealing with an unknown. And if you checked your data table, I'm sure you'd have gotten a carboxylic acid as a possibility for a quaternary carbon in the 180 region. And then you pretty much just plug in your CH2s, right? Your 3 CH2s and your methyl, and clearly your methyl was the most shielded, so you know it would be the furthest away from anything that is electronegative. And then our final examples, example 7, suggest a structure for the compound C5H11Cl using the following data. So in this case, we have 5 carbons, however, we only have 3 carbon signals, which suggests clearly that we have some carbons that are in similar environments, right? So without seeing the structure, you wouldn't have known the structure, right? So in essence, looking at this number, this methylene here is at 57.3, right? That should ring a bell to you, or if it doesn't ring a bell to you, then you need to therefore check your data. You need to therefore check your data table, right, in order to see, you know, where methylenes reside that are attached to something that is electronegative. And we know that chlorine is in the structure. So you want to first do your DBE, right? And based on our structure here, that value should work out to be 0. So that should tell us that we don't have any double bond, we don't have any rings. And having done that, therefore, I think we would want to attach our CH2 to something that is electronegative. And our CH2 here must therefore be attached to chlorine, since it's the only electronegative atom in the molecular formula, right? And then we're told that we have a quaternary carbon. So a carbon that doesn't have a hydrogen attached to it, right? And so here, and then we're told we have methyls, right? So again, you know, sometimes it's a trial and error. So we want to attach some methyls and just to add them up to see if it satisfies our molecular formula, right? So that is pretty much how you would work it out. And then finally, I don't know if you recall our question from lecture 1. So I have brought it back here for you to attempt at this stage. So having done carbon, having done proton, having done IR, having done DBE, we should be able to propose a structure for this compound. We haven't done UV yet, but the only thing that we get from the UV based on what we have here, strong absorption above 210, is that possibly we have some conjugation. And we don't need to worry about what that means yet because we haven't done UV yet. But have a go at it and try to propose something. Again, we're doing these examples because we want to get more knowledge and to get more experience. Thank you so much for watching. Please attempt all the questions, attempt all of the examples, or work through the examples on your own. So we're at the end of our 4-part series on NMR spectroscopy. I hope this has been useful information.